And this is the first video in our series about dimensionality reduction. And you can think about this video as a motivation of why are we doing the dimensionality reduction in the first place. I'm going to introduce this phenomenon called the curse of dimensionality and what it is. And first, I will give you a high level of abstraction, um, an explanation. Then we're gonna go to math behind it, and we're going to understand what is going on mathematically. So the curse of dimensionality is that when we increase the number of features in our dataset, um, we have to look into what's going on in our feature space. So firstly, the points start to get distant from each other, and it might be a problem, and most of the time it will be a problem for our machine learning models, because the machine learning models are working based on the distances between points. For example, let's say we are doing clustering, or we need a way to classify points. And how do we do it? We measure the distance between points, and then based on this distance, we conclude, okay, these points belong to a specific pattern. But once we increase the number of dimensions, our machine learning model's ability to do it decreases, and we're going to see why. So we're going to first look at this phenomenon, the probability of a data point being in epsilon a proximity of its feature space boundary. What does it mean? If we have a feature that is one-dimensional, we can just describe it on a line. And we denote the boundary as epsilon. So we can give any value to epsilon, and we're going to choose a value for epsilon in our video. And as I said before, we have one-dimensional feature space, and we also have one statement here, and we say that this feature is uniformly distributed between 0 and 1. For a mathematical convenience, but it doesn't mean it holds true only in this case. It holds true for any case. So we have our boundary, and we define our boundary like this. We have epsilon, and we will say that the point is within the boundary if it's within epsilon a proximity of the feature space. So in this first dimensional case, if a data point is here or here, we will consider it as a point that is close to the boundary. And let's look at the probability that the value of x is not within the boundary, which is basically 1 minus 2 epsilon, because basically the probability that our point is not within the boundary is this distance from here and here. And how do we calculate it? We just write 1 minus 2 epsilon. And let's look at, consequently, the probability that x is within the boundary will be 1 minus 2 epsilon. And let's look at the case where we have 2 dimensions. Then, instead of a line, we can write it as an area. And you can see that in this case, the probability that x is not within the boundary is the area of this section. And how do we calculate it? We just multiply the length of on the x-axis with the distance with the this distance in the y-axis, because now the probability is an area. So if we think of this whole thing as a as one, in the area of one, because the probability of a point being here is one, because it's defined within this boundary. But in order to calculate this area, we're going to multiply 1 minus 2 epsilon with itself, which gives us 1 minus 2 epsilon squared. And generally, before that, of course, in this case as well, the probability that x is not is within the boundary of epsilon approximity, we will just write 1 minus this probability. And as you can already see the pattern, and then we can generalize it and say that the probability of x is probability of x being in epsilon approximity in the feature space in d dimensions is calculated with this expression. And let's just plug in some real numbers and see what's going on. Let's say epsilon is 0.001 in case of the dimension is 2, and then the probability of our data point being close to the boundary of the feature space is just 0.4%. But let's say now we have 10,000 features. What happens here is that this value will go to 1 very rapidly. This basically means that if we have 10,000 features, the probability of our data point being close to the boundary is almost 1. So you can see this phenomenon that as we increase the number of features, our features get close to the boundary. Like our feature space becomes sparse. There are a lot of empty spaces in this feature space. So this was one of the things that we mathematically analyzed and concluded. Another thing that we can analyze is the average distance between the points and how they relate to the number of dimensions they have. And again, we start with 2 random variables that are uniform, and they are the intervals between 0 and 1, and x is defined like this and y is defined like this. Data points, basically data points in n dimensions. Because let's say this is data point 1 and this is data point 2, and they are just described by their components in each dimension. And we can look at the Euclidean distance between the points in n dimensions. So basically, the Euclidean distance, the square Euclidean distance we're looking at here, and it's calculated like this. We just subtract each component from their corresponding component from each other, and then we just sum them. This is the square distance, Euclidean distance between n dimensions. And here, what we do, we take one coordinate difference, and we will just come back here and we'll explain why we did it. But for now, we just take the one coordinate difference. What it means is that, for example, let's say if our data points are 2-dimensional, and we are just going to take one component difference, one coordinate difference. Like let's say we have x is equal to x1, x2, and y is equal to y1, y2. Then we'll look at the difference x1 minus y1. or x2 minus y2. And then we're gonna try to analyze the variance of this. How do we get the variance of this expression here, the difference in one coordinate? And in other videos, I've explained the formula for variance. You can find it in my statistics playlist. It's calculated like this. So basically, the expected value of the random variable squared minus the expected value of the random variable squared. So the expected value of the squared random variable minus the square of expected value of x. And let's focus here and try to calculate it. This is basically integral that we take because like x is here in our case is a continuous random variable, and since it's uniform, and that when we try to get expected value of a continuous variable, which is sum over all of possible values weighted by their likelihood. And this is basically a likelihood function. And we know that in uniform distribution, the likelihood of any value from the random variable is equally likely to happen. So that's why for every value it's going to be 1. So that's why we didn't write it here. And we just calculate this integral, and it will give us 1 over 3. So this part gives us 1 over 3. And we don't need to do integral for the expected value of xi because it's basically 1 over 2. You can think about it like if it changes from 0 to 1, and every value has an equal probability of happening, equal likelihood of happening, and then the expected value will be 1 over 2. And then we come back and write, and 1 over 2 is not, it's the expected value squared, it's just expected value. And we write it back here, 1 over 3 minus 1 over 2 squared, which is 1 over 12. And with the same pattern, the variance of yi, it's also 1 over 12. And let's now talk about why did we calculate this individual xi and yi variances, because we were looking for this, right? We were looking for the variance of this expression, xi and yi. And from statistics, we know that the variance of this is equal to the individual variances, variance of xi and variance of yi. Because these variables are not dependent on each other, they are independent variables. And we get 1 over 6. 1 over 6. We calculated the variance of zi is 1 over 6. And expected value of zi is 0. And why it's 0, we just can look at this expression, variance of zi, the same way we calculated variance of xi. And what we see here is that this goes to 0. Expected value of zi is 0 because we use this. Then the expected value of zi is the expected value of xi minus expected value of yi. And we know that they were the same. They were 1 over 2. We calculated here. So 1 over 2 minus 1 over 2 is 0. That's why the expected value of zi is 0. And then we come here. We look at here. This is 0. And then we look at the zi squared, expected value of zi squared. And the expected value of zi squared here is basically the variance of zi, which is 1 over 6. Yeah, because this goes to 0, and then we are left with this. Then we see that variance of zi is equal to the variance of zi, the expected value of zi squared. And then we come up with this 1 over 6. Expected value of zi squared is 1 over 6. And then again, we have this property that for independent random variables, x and y, the expected value of x plus y is equal to the expected value of x plus expected value of y. And then we'll just apply it here. So we had this here, and we were looking for the expected value of this. And instead, looking at the expected value of this entire expression, we can just look at the individual expected values and just sum them. And we know just for one coordinate difference, the expected value was 1 over 6. And then here, if that using this property and the result that we got from here, we can just write it n multiplied by 1 over 6, which is n divided by 6. And approximately, if the expected value of d squared is n over 6, then the expected value of the distance itself will be square root n over 6. So basically, we managed to find how the distance, the average distance between the points is affected by the number of dimensions here. And we can just plug in some values. If these 2, then the average distance between the points is 0.577. And if it's in 3D, it's 0.707. And if it's 1 million, if we have 1 million features, we just calculate this expression and we realize that the average distance is 408.25. So basically, we analyzed that as we increase the number of the dimensions, we analyze the relationship between the dimension and the feature space. So as we increase the dimension, we increase the average distance between the data points. So this is something that we don't want to happen, right? We don't want a sparse feature space. Of course, one of the ways of solving that problem would be to increase the data, the training data, but that is something that we cannot always do because data is not easily available all the time. And in the next video, we're going to talk about some techniques used for dimensionality reduction and how it's done. Thank you.